have your notes here for section 8.2, day 1. And kind of like what we've been doing, finding area under a curve, or area between the curve and the x-axis, we're going to do this with a little twist. We're going to find area between two curves. So I've got this written on the board. If you want to kind of wait until I'm finished and maybe screenshot it, I think it's kind of important. It's a good visual to refer back to if you ever forget how to do area between curves. So what I've done is I've given you the easiest situation to begin with. What if both curves are above the x-axis? So all of the y values on f of x, the blue y's, those are all positive, and all of these y values on g, those are all positive. Let's find the area between the two curves. And then it gets a little bit harder. What if one of our curves is below the x-axis and has negative y values? What if they're both below the y-axis? Then what do I do? Or below the x-axis, then what do we do? So, here we go. Ready? Suppose I do an integral on f from a to b. Do you know what that gets you? An integral for the blue function from a to b. Yeah, it gets you the area under the blue curve all the way down to the x-axis. Too much, right? We don't want this extra stuff right here. So what we want to do is we want to take the area under the blue, gets us all the way down. Let's get rid of the area under g of x, the green curve. So integrate from a to b to get area under f, and then subtract the area under g. And that's just going to leave us with the area in between. So I set up two separate integrals. Notice that both of them are in terms of x. Both of them go from a lower x value to a higher x value. Okay? So the upper and the lower limits are the same. The variable of integration is the same. We can condense this and just write one integral. I can say it's the integral from a to b of this function minus this function dx. You can take two integrals, combine them into one, and likewise you can take one integral and split them. All right, now what if it gets a little bit harder? Ready? All these y values are positive. I want the area between the top function and the bottom function. So when I do an integral on f of x, that's going to get me the area from the function to the x-axis. Not enough. I need more than just that. I need all this. So can I do this the same way that I did the other one? Over there, I did the area under the top minus this. But is that going to take away some area? Think about it. What does this integral, what does the integral get you? The math behind this integral, yeah, it gets me the area between g and the x-axis, but you know, because g is below, the answer to this integral is going to be a negative. Yet, you want to add the areas together. You want to add this positive area. You want to force this one to be positive so that you can add them together. Well, this minus sign is going to do this. The minus sign is going to take the negative value of the integral and turn it into a positive. So yes, the same math that you would do here, you can do if one of your functions is below the x-axis. Pretty cool. Okay? Uh-oh, what if they're both below? What do you need to do differently if they're both below the x-axis? So, first of all, I've written it exactly the same. So this is the same as the previous two. We can change it if we need to. So, here's what's going to happen. I want the area just between the two. Let's do g of x first. Forget the fact that there's a minus sign there. What does this integral get me? When I integrate g of x from a to b, doesn't that get me from the green all the way to the x-axis? However, it's going to be a negative answer. And we want area. I don't want my answers to be negative. I want area. So I need to take this area from G to the x-axis. The integral is going to give me a negative answer, and I want to do that to it to make it positive. Okay, great. So the negative in front of this integral gets me from here all the way to the x-axis, and it's positive. That's fantastic, but that's too much. I've got from here all the way to the x-axis. I need to get rid of this extra space because this is all I want. So that's going to be a negative. That's going to force it to be positive. It goes from the green all the way to the x-axis. Get rid of this. How do I get rid of this? Do an integral on it. What kind of answer are you going to get? What kind of answer are you going to get for this part? Below the x-axis. This guy is going to give you a negative answer. Well, that's good because you can take this negative answer, combine it with this positive answer, and what it's doing is it's actually taking a positive area between G and the x-axis, and it's subtracting all of this. Hang on. It's subtracting all of this because that turned out to be negative. So the same exact math produces, that I've done over there, produces the area between the curves no matter where the curves are. They can both be below the x-axis, one can be above, one can be below, or they can both be above. You need to take your top function minus your bottom function. All right. Now, you're going to need your graphing calculator today and your notes for 8-2 day 1. All right. Now, there is a slight twist to this. So the first thing I want to show you is, remember when you were approximating areas using rectangles. So let's take two curves. Let's say I want to find the area between the curves. Let's say I'm going to ask you to do this with a rectangle approximation. Don't worry, I'm not. I'm not going to make you do it with a rectangle approximation. But if you did, you would draw rectangles from one function to the other. And rectangle, rectangle after rectangle after rectangle after rectangle. And of course you would want to make them, you would want to use as many as possible to get a good approximation. You would want to squish them all together. Very, very thin rectangles. So what you need to make sure happens is you need to make sure each rectangle extends from one function to the other every single time. It hits this function and it hits this function because it's going to be using these y values and these y values. We're going to start with a low x value, and basically what we're doing is we're adding areas of rectangles over and over and over and over and over again until we get to a higher x value. But the integral does all that for us. Okay, so this is going to be an x. This is going to be an x value. Your function, what you write right here is a representation of y values. How do you represent y values? With a function in terms of x. For example, this could be like a parabola, x squared plus 4x plus 7. This is a function in terms of x. So you've got x's as your variable here. You're subtracting the entire lower function. You may need to put an extra set of parentheses in there. This is a function in terms of x, and the dx on the end just ties it all together. You've got, these are x values, these are x's in your equations, and this is dx back here. What does this really represent? This really, if you remember, represents delta x, or the width of each rectangle. These get you the height of each rectangle. This gets you the width of each rectangle. Now, sometimes you're going to encounter two functions, and when you try to imagine drawing rectangles from one function to another, if you draw vertical rectangles, you got a problem here. No. These rectangles don't extend from one lower function to one higher function. So, we're gonna do the same thing, but in a different way. This time my rectangles are going to be horizontal. And so on, and so on, and so on. Right? They're going to be horizontal. Notice you can see I'm going to start low and work my way high. Each rectangle extends from the function on the left to the function on the right. Left to right, left to right. See? Touches each function the whole way through. Now, let me remind you of something. When you do an integral and you're accumulating areas, you want your lower x number to go on the bottom. You want it to be your lower limit. You want your higher x value to be on your upper limit. So do you agree that numbers to the right are higher? X values to the right are higher than x values to the left. Of course. What about y's? Y values up here are higher than y values down here. That's why we want to take the top function minus the bottom function. This is a higher y value than this is. This is a higher y value than this is. This is a higher y value than this is. This is a higher y value than this is. We've got a left function and a right function. This time my rectangles are sideways. So the representation for the width of each rectangle is dy. The width of each rectangle is dy. What's the height of each rectangle? It's going to be this larger x value minus this smaller x value. This larger x value minus this smaller x value. So you're going to make sure that when you're using sideways rectangles, we're going to put our lowest y down here. That would be this guy. Lowest y down here. Highest y up here. That would be this one. Now, this is going to be right side x values represented in y terms minus left side x values represented in y terms. This is going to be a y. This is going to be a y. These are going to be y's. These are going to be y's. This is dy. So when we need to draw sideways rectangles, everything changes, and now everything is in terms of y. Let's try a couple. We've got one of each here in our examples. It already gives us the two functions. It tells us where to start and where to stop. And let's just make sure that with these two functions, if I draw vertical rectangles, just double check to make sure that each rectangle touches the lower one and the upper one. Yep. Or you know what? I could do it really quick and draw a lot of them and just make them super skinny. They're so skinny you can't even hardly see them. Anyway, so I'm going to go from the low x to the high x. The higher function minus the lower function dx. These y's are higher than these y's. This y is higher than this y. And I'm going to round to 3, and I get approximately 0.707. Moving on. Find the area between the two functions. Watch what happens if I try to draw vertical rectangles. It goes from blue to pink, blue to pink. Good so far, good so far, good so far. Uh-oh. No. The rectangles over here would go from the top. It's the same function. Vertical rectangles are not going to work. So scratch that idea. Let's use horizontal rectangles. There we go. Horizontal rectangles. So the height of each rectangle goes from here to here, here to here, here to here, here to here. Notice that all of the pink x values are bigger than the corresponding blue x value. This x value is bigger than this one. This one is bigger than this one. This x is bigger than this x. This x is bigger than this x, and so on. This x is bigger than this x. We need to make sure we take the pink function, the one on the right side, minus the blue function, the one on the left side. So I'm going to go. Notice my rectangles start low, and I'm going to accumulate. We're like stacking rectangles, sort of. Accumulate all the way to here. So I'm going to start with a low y value and go to the high y value. Pink function needs to be in terms of y. Pink function needs to be in terms of y. Oh, good, it is. It is. It says x equals y plus 1. This is in terms of y. Minus the blue function. The blue function needs to be in terms of y. It kind of isn't. Let's see, did they solve it over here? Oh, they did. They did solve it. So this is the unsolved version. This is the parabola, but then they went ahead and solved for x. So over here, it is in terms of y. All these x's are represented in terms of y. So I'm going to do minus 1/2 y squared, what was it? Minus 3. dy. Very important. Make sure this matches with these, which matches with these. These are y's, this is y, this is y. Now, of course, when you're typing this in, you can just pretend they're x's and use your Math 9 option on your graphing calculator. You can leave it like this and use a double set of parentheses, or you can, distribute your negative, maybe collect a few like terms. Some of you are better at manipulating algebraically than you are with technology, typing stuff in your calculator, making sure you've got the proper number of parentheses and stuff like that. It's up to you. You know what your strengths and weaknesses are. You can type it in like this or simplify it a bit. Either way, I got no, I didn't get approximately. I got 18. 18. All right, there you go. Use your graphing calculator tonight.